All right, so really important evaluation of nuclear material is what's known as the half-life. And the half-life is the amount of time it takes for half of the radioactive material to decay. Okay, so what that means is, let's say you start out with 1,000 radioactive isotopes, or 1,000 atoms. Right? However long it takes for that sample to decay to 500 atoms is known as the half-life. In a second half-life, or the amount of time, that same amount of time has passed since the 1,000 atoms has decayed to 500. In the second half-life, the sample will decay to 250 atoms. And so on and so forth, from 250 to 125 atoms. Now, this idea of half-life can be used for any type of reaction, including chemical reactions, but it is very common and useful in nuclear reactions. Okay, it's useful because you can calculate how much of a radioactive substance will be left after, so much time, if you know the half-life. So, for example, the half-life of iodine-123 used in nuclear medicine is 13 hours. How many milligrams will remain after 39 hours if the original sample contained 35.25 milligrams? Okay, since 39 is a multiple of 13, this problem is going to be pretty straightforward. If we wanted to figure out the number of half-lives, we could divide the amount of time, 39 hours, divided by the half-life. And we will see that 39 divided by 13 is 3. So we could rewrite this half-lives, or half-lives, I guess. We could rewrite this equation. How much of this iodine-123 would be left after 3 half-lives? So we can do this in a couple of different ways. One very straightforward approach is to calculate how much radioactive isotope would be left after each half-life. So if we start with the first half-life, okay, say 13 hours has passed, how much of that original 35.25 milligram sample do we have left? Well, we can just calculate that by dividing 35.25 divided by 2, and that will give us 17.625. But with 4 significant figures, we'll have to cut that off to 17.63. All right. So one half-life has passed, or 13 hours. How much will be left after a second half-life, or 26 hours? Well, we'll just take that 17.63, divide that by 2, and we get 8.815. So if this question had asked for 2 half-lives, that's how much would be passed. Okay, but of course we got to do this one more time, and another 13 hours has passed, so a third half-life, and we just take our 8.815, divide that by 2, 4.4075, or 4.408 milligrams. So after 39 hours, this sample has gone from 35.25 to 4.408 milligrams. Another way we can do this is that if you know the amount of half-lives that has passed, we could calculate it by multiplying our original sample times 1/2 raised by the number of half-lives, which in this case would be 3. Because essentially what you're doing in each of these calculations is you're dividing by 2, or multiplying by 1/2. So if I multiply by 1/2 1, 2, 3 times, that is the same as multiplying by 1/2 raised to the 3. Okay? And so, in our calculator, we should get 35.25 times 0.5 raised to the 3rd, and we should get the same answer. Well, we got pretty close to the same answer because we were rounding off our answer to significant figures each time. We got a slightly different answer, but that's certainly within the experimental error of these measurements would be anyway, so these are essentially the same answers. So that's the 2 ways that we can do this type of problem. Either directly by going each sequential half-life, or by using this type of equation. Okay, here's another type of problem that we can use half-lives for. Determining how long it would take until a sample decays to a certain amount. So in this equation, we've got technetium-99. That's a gamma ray emitter, so you often see the M after it. For metastable, the half-life of this radioactive isotope is 6 hours, and so this question asks how long will it take for the sample to reduce to 3.125% of its original mass. Okay, so this is just essentially asking if we start off with, say, 100% of our sample, whatever the amount is, we know that in 6 hours we will have 50% of our sample. We can do this again to 25, and so this is essentially asking how long is this going to take to get down to 3.125%. And these are usually multiples of whole half-lives, not fractions of a half-life, to keep it simple. So let's just carry this forward. So another half-life would give us 25%. Third half-life would give us 12.5%. The next half-life would give us 12.5 divided by 2, 6.25%. Do that one more time, and we can see that that is how long, that many half-lives have gotten us to 3.125. So that is how many half-lives? 1, 2, 3, and then 4 half-lives. And if each half-life is 6 hours, 4 times 6 is 24 hours. And so it would take 24 hours or 1 day for this sample to decay to 3.125% of its original sample.